Okay, so today we're doing interesting collaboration. I have the pleasure of being here with Eddie Matuszak. And we were talking, and I was asking him various things about how he learns material and how his learning process. And at some point I asked, wouldn't it be interesting, would it be okay if I could just watch you learn some material, just sit beside you? And you suggested, why don't we make a video of this so other people can benefit as well? And so that's what we're doing. And we're starting here with David Griffiths' Intro to Quantum Mechanics, proof that it's not pirated right here. And yeah, I'm just very curious how you approach material, how you figure out where you're confused and what's interesting and what to look further into.
Cool. So I guess I've been doing research on the opportunities for like a particular kind of learning practice to really reinforce learning. This is usually referred to as like spaced repetition. I often call it just memory systems. And we'll be looking at a prototype I've made that'll let us look at this book while I use this unusual practice. The general idea and what I'm going for here is that like we're going to be reading some quantum mechanics stuff. This will be cold for me. And I anticipate this will be difficult for me. I last studied quantum mechanics 16 years ago. I looked at it briefly during my collaboration with Michael Nielsen a couple years back when we were working on quantum computing. But like to be clear, he was the expert there. So this is cold for me. I read the preface where Griffiths talks about linear algebra requirements, and those are also about 17 years out of date for me. So we'll see how this goes. I think it's going to be hard. And because I think it's going to be hard, I think I'm going to need help. So I'm going to lean on various tools for help. I'll lean on GPT-4 if that seems useful. But mostly I think what's going to be hard is like there's just going to be a lot of new stuff very rapidly getting thrown at me, and I need to internalize this stuff. And one way to do that is by doing a bunch of practice problems, and we're going to do a little bit of that, assuming that we get there. But in order to have a decent experience doing those practice problems, and in order to make good use of time, I also need to just have internalized the core terms, the core concepts, the ways that they relate to each other, the properties of things, notations. There's a lot of notation in this book I can see already just by glancing at it. And I don't want to be in a position where like I'm looking at these problems and trying to just like figure out what does this variable mean. So anyway, we're going to be using this memory system stuff as I go. And the idea is that I'm going to be writing little tasks for myself as we read that try to transform the knowledge in the book into tasks that make me retrieve or use or do something with that knowledge so that I internalize it more effectively. And I will practice those tasks as I read to make sure before I go too far, a few pages beyond a new idea, that I have indeed internalized it. But I'll also be carrying these tasks with me in subsequent weeks so that ideally, if we talk about the content of this chapter in a month, I will still be able to talk about it confidently. And that is like not my experience. Well, when I studied quantum mechanics 17 years ago, I think probably 3 months after that class ended, it was like completely out of my head. Maybe 3 days. I don't know.
Yeah, that's one I'm especially eager to learn more about. When I'm learning material, I think I'm going to learn a lot more about just how to process material as you're going through it. But one area that I've not focused on at all when I'm learning any material is how do I make sure that I've retained this or that I have set something up for myself that in the future I can reinforce what I've gotten out of this session. So yeah, I'm very interested. And I'll just be throughout asking questions, probing about, what you're thinking and what your process is. Okay. Yeah, I'm super interested. This is going to be very useful for me.
Let's dig in. I'm going to get started, and we can just read this together. I think you've maybe read this chapter already, you told me. So hopefully it won't be too boring for you. I haven't. So right away, the strategy that this book is making in explaining what is quantum mechanics and how do we think about its fundamentals, it's defining them by contrast with classical mechanics. It's saying we think about things this way in classical mechanics, and in quantum mechanics, we're going to think about things in that way. And there's some fairly unfamiliar notation already and representation already for me. I don't actually know if it's important, but I want to be comfortable while I'm reading this book. So I'm going to already just make a few notes in the form of these retrieval practice tasks just to make sure that I'm comfortable with the notation that he's going to be using. One thing that kind of surprises me is that he defines, or he uses, the symbol V for potential energy. That's pretty unfamiliar. I'm used to using U, and maybe that's standard in quantum mechanics, but I just want to know that as I go. So I've made my first little task here. And this is also a very unfamiliar way of looking at force to me. F equals ma, like, okay, that's familiar. F equals minus partial v by x, less familiar. And I'm looking at this and trying to understand. The first thing I do is substitute a u for the v. I'm still in this space of like, okay, it's potential energy. Does this make sense? Really? Force is negative partial potential energy by x? And what I want to do is kind of like plug in something that I know. I guess like we can think about it in terms of kinetic energy. Think about potential in terms of I throw a ball up into the air, starting with some initial velocity, and all of that kinetic energy gets transformed into potential energy at the peak. And so we can think of that potential energy in terms of 1/2 mv squared. And if we take the partial of 1/2 mv squared by x, then in fact we get ma, because the derivative of v is a, and the squared term gives us a factor of 2 on the outside. So that's pretty interesting. I'm gonna make a couple of notes for myself here. Okay. Express F, force, in terms of potential energy, V. That's a pretty unfamiliar thing for me to do. And I'm going to use a cool trick here. This is a tool called MathPix that lets me rapidly grab LaTeX from my screen. I'm a big fan of this. Something weird is, okay, there we go. This is pretty unfamiliar, so I want to make sure that I've internalized it. I'm not yet sure if it's important, actually.
I'll make a note here that one thing I find interesting, when I read through this, I didn't pay that much attention to, do I really understand what the relationship between force and potential energy is? I think I probably just thought, the more potential energy there is, it's like the higher you are in air, more force will be applied. But I really didn't think, can I map the potential energy function from classical mechanics to what's happening here? So I'll just note in here that I wouldn't have noticed that my understanding was as murky as it actually is here.
Yeah, and actually I need to qualify this. So I think this is only true for conservative systems. That's what the text implies. I don't actually really understand that. Why is it not true for non-conservative systems? I think it's because the work energy theorem is not true for non-conservative systems. This is something I don't understand very well. But anyway, I want to make sure that I'm learning the right things here when I practice. I also want to write just a little bit about this derivation, just so I remember. Okay. I don't totally understand what's going on with the negative sign. I think that comes from work is defined as the negative of the derivative of potential energy, and we're getting force from work. I'm not going to worry about that right now. Clearly my memory of mechanics is a little weak, but I am going to reinforce these things. I just want to make sure that I know. This statement about Newton's law follows directly from the others. And I can see already that we're kind of setting up some kind of correspondence between this definition of the Schrodinger's equation and this expression of Newton's law. So normally I think I wouldn't bother to practice this form of Newton's law. But I think I might, given that there's this parallel being drawn with the Schrodinger equation. So I might need to really have this in my bones in order to really internalize the form of the Schrodinger equation. So I'm going to wait. One thing I often do when I'm reading is like make multiple passes and like pull stuff out that's unfamiliar that I can tell that I'm going to need. I'll make like a second pass where it's like I have a clearer picture now of what I think is important or what the author seems to think is important, and now I can form better opinion about what's needed.
Mm-hmm.
Okay, this together with appropriate initial conditions, typically the position of velocity t equals 0, determines x of t. Nothing surprising there. Okay, so quantum mechanics approaches the same problem quite differently. What we're looking for is the particle's wave function. We don't know what that is yet, but we get a definition for it, which is like, it's an interesting narrative choice. We're told there is a thing such as that is called a wave function. We're kind of told to treat it a little bit as an unbound variable in our minds, and this is how it's defined. And there's an analogy being drawn between this equation and the equation above. And let's see if we can understand this analogy. So in Newton's law, we have m second derivative of x by t, partial derivative. And in the Schrodinger equation, we have negative h bar squared over m. So there's this m term again. The constant is rendered differently, but again with the second derivative of phi or psi? Psi. Which is it? I should know that. I studied ancient Greek. We can get an answer. It's psi. Okay. Okay, so second derivative of x here, second derivative of psi here. And actually, I notice now, okay, this is a little more complicated than I thought. So this isn't a partial. This is derivative of x by t, i.e. acceleration, second derivative.
Yep.
And this is partial of potential by x, presumably because potential can vary with time and other things as well. And here they're both partials. I think I hadn't quite noticed that on my first read that the thing we're taking the derivative by, we're looking at how x varies with time on the left side, and we're looking how the potential energy varies with position on the right side. I think on my first read I thought like, oh, this is like a differential equation where maybe we have the second derivative of x on one side and the first derivative of x on the other side, and now we're trying to solve it. It's not that, because we're looking at variation with time on the left and with position on the right. So it's actually something very different. Okay, but we have the same pattern here with Schrodinger's equation. Sorry, you were going to ask something?
No. Go ahead. With
looking at how psi varies with time on the left and looking with how psi varies with position on the right. And there's another interesting difference, which is that in Newton's law, we look at how x varies with time and how potential energy varies with position. And here we look at how the same thing, psi, the wave function, varies with two different quantities, time and position. So there's some kind of structural correspondence between the two, but there's also some differences. And that's pretty interesting. I don't understand these correspondences well enough to like make practice problems out of them or anything like that. So at the moment, I'm kind of just noting them, and I'll see how they evolve in the text. I do want to just go ahead and memorize the Schrodinger equation, and that's going to be a little bit of a difficult task. So let me go ahead and pick it up on my pasteboard here. Schrodinger equation. And let me just look at it and see if I can see any structure that might help me memorize this. Well, first off, let's make this less unfamiliar. Okay, how do I type that? Is it \h bar? Yes. And that question is ambiguous. So the reason why I changed this from what is to what is indicated by is that I want to make clear that I'm not asking for the value right here. I haven't decided yet whether I want to memorize that. I might. And it's interesting that Planck's constant relates to his original constant, which doesn't have the bar in it, by 2 pi. I don't yet know if that is important, so I'm going to hold off on that relationship. If I see the original constant show up later, I'm going to want to make sure that I really have internalized that relationship. Okay.
Yeah, I'm just going to point out. I mean, this is basically what I said earlier, but what is really interesting to me. I think I just basically just read this as is, and I noticed, with Newton's law, we have some relationship between how something is changing with respect to time, with how it's changing with respect to position. And I know I can see in Schrodinger's equation, we also have something like that. And I didn't really think at all about how concretely, what concretely is a similarity other than you have the same thing at the bottom of the derivative. I think that's really interesting that you're really meditating on the textbook wants us to think that there's some relationship. It wants us to understand it. What actually is that relationship?
Yeah, and I don't totally understand it yet. I'm kind of hoping that they're going to play it out, because right now I'm inferring a bunch of stuff. I'm going to write myself a little question. Okay, just about this book thinks it's very important, the analogy between the two.
Yeah.
And I want to give myself a chance to internalize that.
Yep.
I don't totally understand it yet, but by writing a question about it, I'm giving myself the opportunity to return to this question in the future. And maybe my understanding will be better, and I'll have new and different answers, and I'll probably revise the question or split it into a bunch of different questions. So relationship is a weak word right now. The role of Newton's second law and the Schrodinger equation.
Oh, see, I didn't realize this was part of your process, that you can create a card without knowing what the answer is yet.
Yeah, I'm going to sketch an answer, and I want to rehearse it.
Right.
But my rehearsal will get better. My answer will get better.
Mm-hmm.
And I'll probably split this into a whole bunch of different questions as I understand different facets. Okay. Just as Newton's law lets us solve for x of t given initial conditions, the Schrodinger equation lets us solve for the wave function. Both describe the what? Something, and not the position of the particle. We don't actually know what the wave function is yet. Tell us essential properties of the particle's behavior. We don't understand this well yet. Okay, that's kind of where we are.
Yep.
This is a really small number. Just noticing that. The joule seconds. It's interesting. Constants are often awkward in units. Okay, so we've looked at half of a page here, right? It's taken us 10 minutes, 15 minutes. There's other things that we could notice or write about, like the nature of the initial conditions. It's interesting that with Newton's law, we look at the position of velocity at time zero. Usually here we look at c at time zero and x, for arbitrary x, I guess, because it's a distribution. Mm-hmm. But it's a usually, and I don't really understand the significance of that yet. So I'm going to hold off on writing any questions.
Well, let me ask you, I don't know if this is a good point to ask this question, a sort of a meta question. One approach could have been, somebody could have said, I'm just going to kind of read this. I've just started this textbook, so I don't think I'm going to understand it, obviously.
Yeah.
Let me just read this. I'll see this equation.
Yeah.
Maybe there'll be a problem nearby where I can really interrogate this.
Yeah.
Why start interrogating your understanding now as opposed to the other approach?
Well, that's basically what I'm doing.
Yeah.
I don't feel like I really understand this now. I'm kind of just reading it. I mean, we could talk about what is my goal here? So I'm approaching this with the goal, and I'm writing prompts, by the way, for the goal of I'm imagining I'm trying to learn this material quite thoroughly. Mm-hmm. Often when one picks up a book like this, one is not sure what one's relationship to it is exactly. Am I trying to learn this thoroughly? Maybe you're evaluating the book. Maybe you're deciding what is it that one would learn if one were to study this. But I'm kind of simulating and trying to learn this thoroughly. So this is a lightweight first pass. I don't really understand what's important yet. So I'm kind of just reading it and pulling out stuff that seems obviously important. But there's a lot more material in here that I'm kind of not yet engaging with. Textbooks are dense. You know? I don't know if that's a satisfying answer. But, okay. Let's see how we're doing. I'm going to go and just make sure I've internalized stuff well so far. Okay, so just as Newton's second law characterizes the position of a particle over time given initial conditions, the Schrodinger equation characterizes the wave function of a particle over time given the initial positions. V is potential energy in this book. This is the Planck constant. Schrodinger equation. Let's see if I can do any of this. This will probably take me a few tries, so I'll kind of repeat this to get it into my head. On the left side, we had partial psi by, let's say, time. It was multiplied by a constant that involved Planck's constant and I, something like minus I Planck's constant. And on the right side, we had mass in the denominator. Let's say Planck over 2m, h bar over 2m, double partial psi by x plus something representing the initial conditions, which will be v psi. Hey, I said there was a negative sign on the left side, and it's actually on the right side.
I am really impressed because up to the end of the chapter, I was still skimming back, scrolling up to the beginning of the textbook to see that equation.
You need to know this equation.
Right.
I remember enough about QM to know that you need to know this. So I'm going to know it.
Right.
Okay, so I didn't remember that perfectly, so we're going to see it again in a moment. Express f in terms of v. Right, this is a pretty interesting thing. Okay, so we can express f in terms of v as f equals negative partial v by t. I still don't understand the negative. No, by x. Why is it by x? Okay. So this is a function that lets me kind of jump back to the appropriate place in the book. My analogy here is wrong because I was thinking of taking the partial of v very informally. I was thinking like, okay, v is the first derivative, take the second derivative, you get a. But v is the derivative of x by time.
Mm-hmm.
And this is the partial of v by x. So this analogy doesn't work. Okay, so I don't actually really understand this. I don't understand why the negative sign is there, and I don't understand why the partial x is there, and that means that we go to GPT. Okay. Yeah, so I remember this had something to do with the work energy theorem. Okay. The work is minus delta V. Okay. Yeah, this makes sense. So, okay, the relationship at root comes from, yeah. Ooh. Ugh. You can see my prototype's a little janky here. At root, this is where the relationship comes from. Okay, that makes sense. This is a new bug I introduced right before this conversation. The danger of demos. What was I saying? Okay, great. Now I think I understand. Now I understand where the negative sign comes from.
Is a V in the work energy theorem, is that potential energy too?
Yeah. I don't know if this is. Because it's equal. Okay, the work energy theorem says that the work done by a force on a particle is equal to the change in its kinetic energy, and the kinetic energy will be the negative of the change in the potential.
Okay. No. Sorry, I know this is for you, but I never internalized it myself. What software is the one on the left, by the way?
This is called Machado. It's one of the many
GPT wrappers.
Yeah, I like native Mac apps. Okay, back to the review. Okay, it is I h bar times partial psi by time equals negative h bar over 2m double partial c by x plus potential energy times c.
No, I have a question. If you had read that section without remembering much of classical mechanics, you wouldn't have even remembered, here's the work energy theorem. Was that what it was called?
Yeah.
Then how would you have how would you have approached that if you didn't remember that?
Right, that's a good question. I would have said, okay, this book is trying to create a connection, a familiar connection, using something I don't understand. So it's offering a piece of help. It's saying, like, if you understand this thing from classical mechanics, this will help you, because now you can think about this new thing in terms of that.
Yep.
And so I would have said, like, well, this doesn't help me because I don't actually know that. So I would kind of like make some mental note of, like, this is a thing that I don't understand, and hopefully it isn't important. And if too many of those came up, I would probably get scared and like go review what it thinks I should use, or I should use a different book that doesn't try to explain this stuff in terms of this other stuff that I don't know,
right?
Which may not be possible. I don't actually know. Okay, express f in terms of v. F is minus partial v by x. My mistake last time was thinking partial v by t, and that comes from the work energy theorem. And my little thing doesn't update immediately when I edit the thing. Okay. Great. Back to the book. Great. What is this wave function? Yeah, indeed. I would like to know that.
This is like the third time I'm emphasizing this, but it is just so much different than the way I would approach this, or the way usually people think of reading a textbook. So I just want to emphasize it again.
Great.
Is that I think what would be like 20, 30 minutes in, and we're
like a page in.
Yeah. No, I mean, but I think that's incredible.
A lot of padding here.
Because I had even more probably things that if I went through, I'm like, what am I actually confused about? Like, what do I actually understand?
Right.
For me, I probably should spend an hour on the first page.
Well, but like also, what's your goal?
Right.
I mean, like, are you trying to really learn this?
Yeah, but if you aren't, why are you even bother reading it?
I think that's a reasonable question. Like, I mean, I think you might be answering the question, like, what is it that quantum mechanics does? Or like, what is it for? Like, what kinds of things are in quantum mechanics? What does one do with quantum mechanics? And you can get a sense of that by reading through this. Okay, what is this wave function? What does it do for you once you've got it? Sure. Okay, a particle by its nature is localized at a point. And by the way, this footnote kind of throws me. I'm not really going to worry about it. Magnetic forces are an exception to this claim about conservative systems. I'd forgotten that magnetic forces are non-conservative. I think that's because they act orthogonally to the particle. But I'm going to just not worry about that for this moment. It seems like it's not important. Whereas the wave function, as its name suggests, is spread out over space. Kind of suggests that. It's a function of x. This is a big difference, right? Like, so we're used to, in classical mechanics, thinking about x of t, v of t, a of t. And so a really important property of the wave function, actually, is that it's over x. So you wouldn't want to get the wrong impression and think that these figures, like figure 1.2, the x-axis represents time, like it would in most classical figures. But here it represents x. So I'm going to write another prompt, which is about...
What represents x and t, right?
No. I don't think so.
Did you run this wave function xt?
Yeah, no, I mean, in figure 1.2, the x-axis just represents x, and we're seeing a snapshot of time.
Right. Yeah.
But in my question up here, I said that the parameters are x and t.
Yeah.
It varies with. How can such an object represent the state of a particle? The answer is provided by Born's statistical interpretation, which says that the magnitude of the wave function squared gives the probability of finding the particle at point x at time t, i.e., the parameter tuple, or more precisely, and now we have this integral definition. Okay, if you want to know the probability of finding it between positions A and B, you would integrate that quantity.
Yep. Okay.
I'm going to write a few prompts about that, but first I'm going to kind of finish reading this section because I want to see how it ties this into figure 1.2. For the wave function, okay, probability is the area under the graph of c squared. Right, if we're looking at c squared by x. And that's why it makes sense to use an integral here. For the wave function in figure 1.2, you'd be quite likely to find the particle in the vicinity of point A, where c squared is quite large, and relatively unlikely to find it near point B. Okay, yeah, great. Okay. Let me think about what I want to take away from this section. There's a few obvious things to take away. What is Born's statistical interpretation?
By the way, is this PDF software you're using, is that open source? I mean, I know you wrote it, but is it something other people can find on GitHub or something?
It probably will be, but at the moment there's a lot of hacks, and so it's not quite live. Yeah. Various parts of what I'm showing are up on GitHub. Okay.
This is really cool.
Okay. Okay, I'm gonna encode this one a different way. So this makes sense. Yeah. But we need to interpret what it means, magnitude. PDFs are terrible. Okay. Right. Yeah, so it's not a scalar. We can't just square it.
And I presume you already know why it has to be the complex conjugate, or if not, you would have gone through and looked at that. Okay.
It's just like, it's easy to forget that C is complex. Okay, there's a few other things of interest here. These figures are pretty evocative. I'm just trying to think, like, I think I want to give myself some challenges about understanding these figures. I'm trying to understand what I want those to be. Right. Okay. Yeah. I think this is the kind of move I want to make. So I'm I want to make sure I understand this visual interpretation, this relationship between the statistical interpretation and the geometric interpretation. Okay.
As a side note, well, one question I had for my tutor when we got to this section was that I noticed was, the only thing I understand about the wave function is at this point is that, if you square it, you get the amplitude or the probability that it's somewhere. But what does it intrinsically mean? Like, why is the wave function itself? Does it have any other meaning other than the square root of the probability? And we talked through that. I mean, we can talk about that later, the actual meaning, but that was something that I noticed on this page.
That's quite interesting. Yeah. What is this? I'm still in the space of, like, I guess my intellectual, like, stance towards the wave function right now is like, this is an abstract quantity that this author is defining for me. Yeah. And like, it exists insofar it is useful as a symbolic quantity. and like, let's discover various ways in which it is useful.
Yep.
And so we have one of those ways, and actually it answers an important question, which is like, and this is another one of these questions, which my answers will evolve over time. So it's not a very precise question. This isn't really like a memory practice question per se. This is like a question that gets me to like think about what I know about this, and maybe to draw some new connections. But initially, I do actually want to just remind myself that, yeah, that the wave function can tell us where a particle is likely to be in space. And I'll use EG to indicate to myself that like this is just one possible example, but there's lots of interpretations that are likely interesting or useful.
Well, actually, I'm not sure. I mean, I've only got through just the chapter 1 of the problems here, so I'm not sure if anything I say should, but one thing I'm wondering about is that would that be an accurate definition by the end of the chapter? Because
I don't know.
Well, one thing I'm wondering is because if you just got the amplitudes, right, just psi squared, that would tell you where the particle is likely to be. The reason the actual wave function is relevant is to tell you how it will evolve, which you can't get from psi squared.
Yeah. No, I think that's right. That's a better definition. But I hadn't really realized that yet. So I'm gonna leave it for a minute and see. Is there something later in this chapter that makes me more aware of that? Because I'll like use that as a trigger to go like refine this question, or I may actually refine it. Like naturally, if you hadn't said this, I may have refined it when practicing it rather than like explicitly going back. Okay, indeterminacy. Okay, statistical interpretation introduces a kind of indeterminacy into quantum mechanics, where even if you know everything the theory has to tell you about the particle, its wave function, you still can't predict with certainty the outcome of a single experiment to measure its position. All you get is statistical information, right? Yeah. Right. How do I want to encode this, or do I want to encode this? I'm not sure that I do. I feel like this is something that I actually understand pretty well. I'm not sure that I do. Okay, suppose I do measure the position of the particle and I find it to be at point C. Where was the particle just before I made the measurement? Okay. So these are about interpretations right now. And I'm kind of, at a metacognitive level, I'm thinking about, what is this for? So the content so far is like giving me the tools that I need to understand any kind of discussion of anything about quantum mechanics. This is a technical definitional discussion. Here we're to interpretation. What does this stuff mean? What is it for?
Yep.
How should we think about it? It's not in the same kind of tool space. Okay, the realist position. The particle was at C. Where was the particle just before I made the measurement? Okay, it literally was at C. We measured it. We found it was at C, and therefore it was at C immediately before we made the measurement. Okay, if this is true, quantum mechanics is an incomplete theory, since the particle really was at C, and yet quantum mechanics was unable to tell us so. Right. That's very interesting. Indeterminacy is not a fact of nature, but it's an epistemological fact. The position of the particle was never indeterminate, but was merely unknown to the experimenter. C is not the whole story. Some additional information, such as known as a hidden variable, is needed to provide a complete description of the particle. That's very interesting. Okay. Let's see. How do I want to ask this? Yeah, okay, but more importantly, these details about the consequences of that belief. Yeah.
One thing this makes you curious about, or something to read after you're like actually done studying the textbook, is where do people who hold this position think hidden variables are? Like, in what way do they think it's? Yeah, where would they find the inadequacy?
I'm aware enough to know that there have been a bunch of experiments on like constraining, like what kinds of hidden variables could they be, but I don't know the secrets or the details. Okay. I don't need this because I should say for people familiar with spaced repetition systems. So I'm not giving context to any of these questions because when they appear in my reviews, they'll appear with a line above that says Griffiths chapter 1.
Oh, okay.
So I can just say what's meant by a hidden variable, and I'll see Griffiths, and I'll say like, okay, we're talking about QM here.
And when you do these, when you do reviews, do all the questions from all the different things are coming up come together?
Yeah. There's actually some interesting CogSci support for this kind of interleaving that suggests you learn stuff better if you mush it all together. All right, what is meant by a hidden variable? Okay, there's probably more to what's meant than this, but here's like a first sketch. Okay. All right, the orthodox position. The particle wasn't really anywhere. The act of measurement forced it to take a stand. Though how and why it decided on point C, we dare not ask. Jordan said it most starkly. Observations not only disturb what it is to be measured, they produce it. We compel the particle to assume a definite position. Yikes. This view, the so-called Copenhagen interpretation, is associated with Bohr and his followers. Among physicists, it has always been the most widely accepted position. Note, however, that if it is correct, there's something very peculiar about the act of measurement, something that almost a century of debate has done precious little to illuminate. Indeed. Yeah, I'm realizing this is really interpretations of measurement. Yeah.
One question I have about the pace is, if you want to learn a new subject, is this something you price in? That like, if I want to learn it, it's worth learning in this way, and if I learn it in this way, this is a multi-month endeavor. And does that influence what you're willing to take on as a project?
So I don't necessarily learn everything this way. Like I learn things that I'm trying to actually learn this way. I guess because I think that that's what's actually entailed. And I guess my perspective is more or less that like my history of learning things in not this way were some combination of like fooling myself and actually like not really understanding the thing, or ending up learning this way, but through like a bunch of like kind of bumbling during like doing the problem sets. I end up kind of flipping back and forth, and like in conversations with people like what was the orthodox position? Like, how does that relate to the Copenhagen interpretation again? You know, I kind of end up like doing this, but like implicitly over a much longer period of time. And sometimes that's better because you kind of let the situation draw out the knowledge or the reinforcement. It's more natural in some ways. So if I'm not really sure about my stance towards a topic, like I'm not really sure if I want to learn it seriously, I'll often just kind of let natural reinforcement happen. But if I really want to learn something, this is like a very direct and reliable way to learn it. So you asked, okay, right, and you said multi-month. Would it be multi-month? Maybe. This is a 400-page book. and we're at about, call it 15 minutes a page.
Yeah.
That's a pretty significant commitment. It's 100 hours. I don't know if 100 hours is multiple months. Probably in practice, probably 5 weeks, 6 weeks.
And another way to think about this is, you could do all 400 pages of the book. I think the first 3 are like the very foundation, and then the next 3 are more theory, and then the last 6 are applications. So one way to think about this is maybe it takes you the same amount of time to do it this way for the first 6 chapters or 3 chapters that would take somebody to just like read through 400 pages. But you could just say, listen, I have 50 hours to dedicate. Am I going to dedicate those to really understanding the first 3 chapters, or to reading all the chapters and then not really understanding all of it?
Right. So, I mean, like, for the purposes of this discussion, I am like choosing a gear on the car engine that's like pretty careful.
Yeah.
And like, I do often choose different gears. But it seemed to me like you were interested in like, what does it look like to like really study the thing?
Exactly.
This is, I think, what it looks like. And I guess what's interesting is like, first off, that 100 hours is probably an underestimate because you got to do the problems too.
Yeah.
It doesn't take much time. But second off, like, let's not delude ourselves. Like, you're not going to understand QM in 100 hours.
Yeah.
Like, maybe we say like, that sounds like a lot. You need like a month or 2 months to do those 100 hours. But like, actually, like, your understanding will still be pretty crappy at that point, Now, also, like when I took QM at Caltech, I spent a year on it. I mean, it wasn't 9 months or 8 months or something. And that seemed like a reasonable thing to do. So I don't know. This doesn't feel that slow to me. Like in practice, it would actually be much, much more because of the problems, like I'm saying, and because I'd make multiple passes. Yeah. I'd probably read multiple books, actually.
Yeah. And how come?
Because my experience is that in physics in particular, people take like very different tacks on topics. Different authors do. I haven't studied quantum mechanics systematically enough to have opinions about different books. But it would be unlikely that I wouldn't benefit from reading another text on the subject. Yeah. And that second text, like I would already know what the Copenhagen interpretation is when I read that next text, right? Yeah.
I will also note, by the way, that I think you would solve problems much faster with this approach, and we'll get to them in a second. So we'll see. Yes. So it might. I don't think it would necessarily net out, but it would definitely not be as much. Because if you are just reading through it and then you get the problem and like, what is this equation again? Yeah. Then you're still spending that time anyways with less understanding.
Yeah, maybe. It's not clear that writing these questions, especially and doing the review, actually produces less total area under the curve if you're looking at like maximizing time. The main reason I do it is that my experience has been, and certainly plenty of research has suggested, that my likelihood to actually remember this stuff several months later is very low if I do not do this. Yeah. I will remember the broad strokes if I do not do this, and that's about it. Yeah. Now we're 17 years later, so it's not really a fair thing.
Sure.
But like I said, I think like a matter of a couple of months after. I really didn't know. There's a great study of medical students that sampled them 1 year, 2 years, and 25 years after their medical boards and looked at their decay. And they'd forgotten 85% of what they learned for their step 1 exams 25 years later. Only the stuff for their specialty survived, which like you can interpret that in a couple of ways. Like one way to interpret that is like, that's fine. Like the stuff that they needed in their practice survived. Yeah. Another way to interpret that is like, that's mostly true. But when that patient comes in with that like one disease that you were supposed to learn, but like is very rare, so you never saw it. Like, I don't know, maybe you wish that you had remembered that stuff. Okay. Yeah. Maybe I'll keep chugging so that we can see if we can get through to some problems. Yeah. We'll see how far we get. Okay. Okay. If I thought this was really important, I might code it both ways. I know the Copenhagen interpretation is like a very important term or idea. All right, the agnostic position. Well, hang on. This last sentence is kind of interesting. I'm trying to decide what I think about it. There's something, right. If the orthodox position is correct, there's something very peculiar about the active measurement. Yeah, like definitely. I'm not sure there's anything to practice with respect to that. Like, it feels weird already. Like, when I read this explanation, by measuring the particle, I caused it to assume a definite position. This is just weird.
Yeah. One thing I noticed is that they don't give them any worlds here.
I noticed that too.
Yeah.
Okay, the agnostic position. Refuse to answer. This is not quite as silly as it sounds. All right. What sense can there be in making assertions about the status of a particle before a measurement when the only way of knowing whether you were right is precisely to make a measurement, in which case what you get is no longer before the measurement? It is metaphysics to worry about something that cannot by its nature be tested. That's a very positivist view. Okay, one should... Pauli said a thing. For decades, this was the fallback position of most physicists. They try to sell you the orthodox answer, but if you were persistent, they'd retreat to the agnostic response and terminate the conversation. Okay. I don't need to encode what the agnostic position is because the word explains it. And I'm not at the moment interested in this history. Although it's interesting that there's something implied in this sentence, right? Like, they try to sell you the orthodox answer, but if you were persistent, they'd retreat. The implication there is that if you're persistent, they can't actually defend the orthodox answer. It doesn't say if you I don't know, had different priors, or if you didn't believe them or something. It's just oh no, if you tried to have a real conversation, they'd retreat. I don't know. It's funny. Okay, all three positions had their partisans. Right. This is one of the things I was referring to. Okay, in 1964, John Bell astonished the physics community by showing that it makes an observable difference whether the particle had a precise, though unknown, position prior to the measurement or not. Yeah. Bell's discovery effectively eliminated agnosticism as a viable option. Why? And made it an experimental question whether 1 or 2 is the correct choice. And again, we're not talking about many worlds here. Okay. That is interesting. Okay. Oops. Why can the agnostic interpretation of measurement not be true? True is not right. Not be sustained.
Right. Because I intuitively understand why there's a difference between 1 and 2 here, where if there's a hidden variable, the system doesn't change after you measure it. Whereas but yeah, that's a good question, actually. I'm not sure why 2 and 3 are different here.
It's kind of just implied in the text, and I found that I had to extract it in my mind, and so I wanted to make a note of it. Okay, this is interesting. Yeah, I want to make sure to grab this. I guess it's referred to later in the text, and I haven't read yet, but it'll lay itself out when something else changes. Caches. Okay. An experimental question. Is it experimental? We don't know how to run the experiment. I guess is the problem. Okay, I'll return to this story at the end of the book when you'll be in a better position 400 pages later to appreciate Bell's argument. Okay, for now, suffice it to say that the experiments have decisively confirmed the orthodox interpretation. Really? Because I think that's because there's a bunch of hidden variables are constrained in lots of ways. Basically, is my vague memory. Have decisively confirmed the orthodox interpretation. A particle simply does not have a precise position prior to measurement, any more than ripples on a pond do. It is the measurement process that insists on one particular number and thereby, in a sense, creates the specific result, limited only by the statistical weighting imposed by the wave function. Okay, the statement's a little too strong. Hey, here's many worlds. There exist valuable non-local hidden variable theories. Non-local hidden variable theories, notably bones. I have heard of this, but I don't know what it is, and other formulations that don't fit cleanly. All right. There's that word non-local. I think one of the big results is that if there are hidden variables, they must be non-local, i.e., they changes to them are communicated at faster than the speed of light. Yeah. And that would be a surprising thing if it were true, although one could accept it. All right. What if I made a second measurement immediately after the first? Would I get C again, or does the active measurement cough up some completely new number? Everyone's in agreement. Indeed, yes, this I remember. A repeated measurement must return the same value. How does the orthodox interpretation account for the fact that the second measurement is bound to yield the value C? It must be that the first measurement radically alters the wave function. Yeah, I don't like this. So that it is now sharply peaked about C. This is very inconvenient. We say that the wave function collapses upon measurement to spike at point C. It soon spreads out again in accordance with the Schrodinger equation. Is that in accordance with the Schrodinger equation? I don't really see how.
Maybe one way to think about it, if the Schrodinger equation describes how the wave function evolves, then it just like you go from a point and then it just like diffuses.
I see that that's the claim, but what I'm noticing here is that like I've memorized this function, but I can't visualize anything about its behavior. Like, first off, it's complex. That already makes it hard.
Yeah.
Complex in the literal sense, technical sense. And second off, it varies by two terms, by two inputs. So the claim is that if x, if you look at a particular x where C is very, very large, and the second derivative then would be extreme at that point, and you look at how t changes over time, so if the second derivative is extreme at that point, what you see is relatively extreme changes in t.
Okay, interesting. Yeah, I'd be actually. This is one question I might write down for myself: is that is a change greater than it would be if x were it wasn't concentrated on one place? Like, would the change still happen? It just that it would be.
Yeah. So this informally seems to imply something like the wave function tends to spread out.
Yeah. Yeah, and I don't understand why. This is something I didn't notice. Again, another things I didn't notice while I was reading it that I didn't understand.
A common tactic when reading anything technical is like take the equations and like plug things into them. And so like if claims are made involving the equations, like you want to get a sense of how the equation varies with respect to this variable or that variable, or how it behaves at limits. Like what happens when this is infinity? What happens when this is 0? What do you mean by Monte Carlo?
You just plug in different inputs.
Oh, certainly you can just try random inputs. Yeah.
Or more an analogy rather than actually doing Monte Carlo.
Yeah. I find it more helpful to think about like really, I guess like edge case situations, where you have like all of it's concentrated at a point, or you have like a totally uniform wave function. Like if you have a totally uniform wave function, the second derivative is 0. And so the change over time is constant, we see. Oh, well. No is accelerating because as it grows, it'll grow more.
Although that's not possible because if it was uniform across like infinity and negative infinity, then the probability wouldn't add up to 1. It has to in the limit. It has to go to 0.
I guess that's true. I'm also realizing that I don't actually know what's. Okay, no, yeah. Okay, great. Let's go back. Okay. We say the wave function collapses. Yeah, okay. And then it soon spreads out again. That's pretty interesting. I don't think I want to write a prompt about that just yet. There are then two entirely distinct kinds of physical processes. Ordinary ones in which the wave function evolves in a leisurely fashion, and measurements, in which suddenly, right. And we can see why like physicists don't like this, right? This is terrible. Okay, the role of measurement in quantum mechanics is so critical and so bizarre that you may well be wondering what precisely constitutes a measurement. Indeed, I'll return to this thorny issue in the afterword. That doesn't bode well. For the moment, let's take a naive view of measurements, the kind of thing a scientist in a white coat doesn't okay, I have enough memory of QM to have a somewhat richer definition than that. I also have enough that I don't need to encode the fact that there are two kinds of processes, although I would if it were completely new to me. I don't need to encode anything about collapses. That's familiar. Although this I think I could have come up with, but I want to reinforce this visual. So
Right.
I made a prompt about that. This stuff is pretty familiar.
It actually is quite useful because having read about the many worlds interpretation, just understanding, it's like this is when the system gets entangled. Measurement is when the system gets entangled with the rest of the world.
Yeah.
But if I didn't, this textbook would be so confusing to me right now.
Right. Yeah. This is a thing that I find pleasing about the many worlds interpretation. But again, like I don't actually understand QM, and so like I'm not really in a position to evaluate it. Okay. A thing that was new for me here is that the wave soon spreads out again. I guess I understood that, but I don't know. Okay. Hey, we have an example. It's in a box. Electron interference. I've asserted that particles, electrons, for example, have a wave nature encoded in C. How might we check this? Interference, right. Two waves in phase interfere constructively, and out of phase they interfere destructively. Young's famous double slit experiment. This is a very beautiful experiment. Okay, there's a distinction drawn here between light and electrons, but the distinction is that the two actually behave the same way, I guess. All right. Wow, this footnote 10 is pretty interesting. Okay. Suppose we decrease the intensity of the electron beam until only one electron is present in the apparatus at any particular time. According to the statistical interpretation, each electron will produce a spot on the screen. QM can't predict the precise location of that spot. All it can tell us is the probability of a given electron landing at a particular place. But if we're patient and wait for 100,000 electrons, one at a time, to make the trip, the accumulating spots reveal the classic two-slit interference pattern. If you close off one slit, or contrive to detect which slit each electron passes through, the interference pattern disappears. The wave function of the emerging particle is now entirely different. In the first case, because the boundary conditions for the Schrodinger equation have been changed. And in the second, the first was when you close off a slit. And in the second, because of the collapse of the wave function upon measurement, right? But with both slits open and no interruption in the electron in flight, each electron interferes with itself, right? It didn't pass through one slit or the other, but through both at once. This is a water wave. Yeah. Okay. The thing that's amazing about this, that I want to emphasize for myself, is the fact that this interference stuff occurs when the electrons are alone. Okay. This process of like explaining stuff to myself is of course also a very powerful way to learn. And it's a little bit in contradiction with some of my research, right? Because like I've been researching various ways that like the author could provide these kinds of questions. And like a lot of the difficult cognitive work that I'm doing is in kind of compressing the book and running it through my mind and running it through my own words and like noticing what I'm not remembering.
So this is actually maybe the answer to the question I was about to ask you, which is, one thing I've really noticed you doing is you go through a section and you're like, what do I understand here and what do I not understand? And how do you figure out where it is the point of your model of what's happening is the weakest? Is it just that you try explaining it to yourself and you realize I can't explain this part?
I think I'm constantly trying to explain things to myself. I think there's some kind of process that's constantly saying what the author really means here is X. And it's not that strong. So like it's sort of like a weak version of what happens when I try to write the prompt. Like when I try to write the prompt, there's more pressure on the self-explanation. And what's interesting is that like when I answer the prompt, there's even more. I think we had a good example of that in the beginning when we were looking at this definition of force in terms of potential energy, where I had just kind of like misread it as being partial v by t, and that let me make this analogy to acceleration. And it wasn't until I tried to answer it and realized that I reproduced partial v by t, but no, that wasn't it.
Right.
That I realized, like, oh no, I didn't understand. So there's these kind of layers, I guess.
Yeah.
So I'm just going to run through the section and make sure that I absorb this stuff. The orthodox interpretation is that it didn't have a position before the measurement. Measuring caused it to have a position. I'm using keyboard shortcuts here just to be a little quicker. Visualize the wave function. It's a spike. Why would a realist interpretation of measurement make it an incomplete theory? Because it would mean that the particle had a position immediately before the measurement, but somehow QM couldn't tell us what it is. So you need some kind of extra variable or something. I measure a particle to be at C. What is the realist interpretation? The realist interpretation is that it was there. Okay, given C, how to find the probability of a particle being between points A and B at time t. It's the integral between A and B of magnitude C squared dx. What is meant by the claim that an individual electron has a wave-like nature? Right, this is the fascinating observation that individual electrons will interfere with themselves in a double-slit experiment if you fire them one at a time. Born statistical interpretation is that you can get the probability that a particle is in a particular place at a particular time by squaring the magnitude of the wave function. How to find the probability that the particle has a position between B and C? Take the area under the curve there in this figure. What are the parameters of the wave function x and t? Why can the agnostic interpretation of measurement not be sustained? Because Bell's experiments showed that it matters, actually, whether the particle had a position immediately before the measurement that was precise. So you can't just say, it doesn't make sense to talk about the position before the measurement. Okay, what is the wave function for? I know I'm going to end up revising this answer. It shows us how the position of the particle, the probability of it being in a particular position evolves over time. And that's a better answer than this. The Copenhagen interpretation is also called the orthodox position of measurement. What is meant by a hidden variable? Some additional information that the realist interpretation of measurement needs in order to explain where the particle must have been before measurement. Yeah. How do we actually compute c squared symbolically? It's a complex number, so to take the square, we have to multiply its complex conjugate by itself. Probability. I last seriously studied probability maybe 16 or 15 years ago. And my understanding is like pretty shaky, but it's probably better than my understanding of QM. So let's see what's new here to me. Like a little better, not a lot better. Okay, because of the statistical interpretation, probability plays a central role. Yeah, okay, great. There are 14 people. They're distributed in this way. Let n represent the number of people at a given age. Yep. The total number of people we can get by summing all of the people at a particular age for all values of ages. Yep. All right. Question. I scroll so I can't see the answer. If you selected one individual at random from this group, what is the probability that this person's age would be 15? It would be 1 in 14. Yeah. Okay. In general, right, this is a frequentist interpretation. The probability of being at a particular age is the number of people at that age over the total number of people. Okay, the probability of getting either 14 or 15 is the sum, yes, of the individual probabilities. Okay, the sum of all the probabilities is 1, yes. Okay, what is the most probable age? The mode is 25. What is the median age? Slightly less clear. There's 14 people, so the median age will be, I think, the average of the 7th and 8th person. 1, 2, 3, 4, 5, 6, 7. It'll be 23. Yeah. Okay. What is the average age? Oh, I don't know. I don't feel like computing, but I feel confident that I could.
Yep.
Okay. Am I confident in interesting notation? So, okay. Um, okay. Is the sum of the value times the count of the value over the total. That feels familiar. Okay. I'm not worried about this. Okay. There's another question. What's the average of the squares of the ages? You can't pull the square out. Is there something to do this besides just rote computation? I don't quite understand why I'm being asked. Okay. Why am I being asked?
The reason is it wants you to understand the difference between the average of the squares of the ages and the square of the average of the ages.
Yeah. I do understand that difference.
I figured you did.
Yeah, no, thank you. But then I guess I'm asking that question. That's actually a useful question in textbooks. Now that we're to the point of questions, why am I being asked this question? Because there's something I'm not understanding. Okay, and here they're making the point that you just made. The average of the squares is not equal to the square of the average. Yeah, exactly. I said that a moment ago. Okay, right. The average value of a function of j is given by... Right, the sum of the value of the function at j times the probability that j is in fact the case. Yeah, this is all still familiar. Okay. Conspicuous difference between these histograms. Yeah, they have the same median, the same average, the same most probable value, same number. Okay, this is all also quite familiar. We need a numerical measure of spread in a distribution. We get a definition of the deviation. Trouble is, of course, that you get 0. Wasn't obvious to me that you would get 0. I guess, yeah, okay, you can demonstrate why. Because you can separate the sums. Yeah. Interesting. Okay. I think I don't care enough to remember that. Sorry,
no, it's a bit as well. Why can't you just take the absolute value? Why is the square significant?
I think, right, I wasn't to this paragraph yet. I think it's because absolute values are nasty to work with.
Yeah. Oh, there it is. Oh, I'm sorry. I missed that.
Sorry about that. Yeah. They're not smooth. They're not. They have a discontinuity in their derivative. And integrating them is painful. Mm-hmm. We get around the sign problem by squaring before averaging. Yeah. There's some cute stuff here, actually. That's actually kind of interesting and non-obvious for me. So I'm going to write a couple of cards. Okay. Right. I guess this is the same thing. Yeah. Okay. So variance is the average of the squared deviation. Sigma is the standard deviation. This is all familiar with the letters, the customary measure of spread. A useful little theorem on variances. Okay. Could I derive this? Okay. The claim is that the variance is equal to the average, the squared average. No. The average of the squares minus the squared average. Yeah. So one thing that I'd like to be able to do in my little practice regimen, this is the kind of thing that this is a good little derivation to do. Like if you understand variance and you understand expected values, then you should be able to derive this. I think I would actually need to think about it. I think it suggests something about my non-facility with these things. So just giving myself an exercise, I'm going to go ahead and tackle it right now. I'm not reading any of the intermediate steps because it just feels like an endless slog of symbols. So let's just work through it. I don't know, I'm interested. So we can time box it. So the claim is that, and let's just make sure we're seeing, sigma squared is ultimately equal to the expected value of the squared terms minus the square of the expected value. Is that it? Mm-hmm. Yeah. Okay. So let's prove that. First, let's start with the definition of sigma squared. It's the average of the squared deviations and the deviations are so I'm going to substitute for the definition of expected value. And I'll get this. And now I can substitute in for the definition of deviation. Is this super boring for you? Is this all really obvious? All right.
Well, I read the intermediate steps, but it wouldn't have been otherwise.
I mean, does reading the intermediate steps actually allow you, do you remember the intermediate steps?
Yeah, kind of.
Kind of. All right. I have made an error. Okay. So now we have 3 different expected value terms. This is kind of awkward. Well, I can see already that one of the terms we have is this one. Mm-hmm. And this goes to j squared. Mm-hmm. So I see that we have this term. And I see also that this term will give rise to, the negative sign doesn't seem to match. Okay, well, something else interesting happens, and I don't know what yet. Yeah, and what's interesting here is that we seem to get this second term. We seem to get this second term, but with the wrong sign. And then there's this middle term. So there must be some interesting property we can use of these things that help us out here. Oh. No. Okay, so yeah, I was wrong. So this doesn't actually give us this.
Yep.
In fact, it gives us something weird. It gives us a strange thing. Like the expected value of...
Oh, wait. Yeah, you're right, actually.
That's kind of weird, huh? Whereas this guy gives us this other kind of weird thing. Well, the expected value of an expected value is just the expected value. Right? Like, I'm pretty sure that's the case. Just by the definition, like we could have a little lemma where we demonstrate that. But then I still have this middle term, and also the sign is wrong.
So I think I see, but
okay, throw me a bone. What are you seeing?
What if we broke this apart into its definition?
Yeah, let's give it a try. Is this helpful, Dwarkesh?
Well, I don't know how that's distributed. My broader intuition was this is -2 of this. This is +1.
Oh, okay.
So they probably cancel out.
Right. So I think you're right, and I think we want to make this middle term get to expected squared.
Two times the.
And I think we can two times expected squared.
Yeah.
And I think we can do it. Right. So is it the case? Okay. Right. So we would like it to be the case that in general, when you have a times expected of a, or even a times expected of x, then that is equal to expected of ax. And I recall that is the case.
Mm-hmm. Yep. And
therefore we can just go ahead and move the j inside. I don't feel like proving this. I'm confident that I could. So this guy is in fact equal to, I can just make the leap from here, is equal to minus j squared, right? And now, 2, minus 2j squared. And so these two guys cancel. And it's interesting. So what we use two different properties of expected values here that like I was a little rusty on. I needed to think about them for a minute. Like, is this the case? Yeah, that's definitely the case. Is this the case? Well, it has to be the case.
Right,
it's the expected value of a constant.
Yeah.
Okay. And so this is the kind of thing that like it makes sense to practice doing this sort of proof, but like probably not identically this proof. I think like in my ideal world, I would do like things kind of like this intermittently, but maybe not exactly this.
Well, one thing I'm curious about is, do you have a better intuition about not how you get here, but why it actually is the case that this is the same thing as the difference in between the average and the...
Oh, right. Like, let's think about it visually, for instance. Or think about it like just in terms of spread.
Yeah.
Like, why should spread be the difference between the expectation of the squared values and the average squared? Okay, well, the average... it kind of does make sense. So that it's a little bit like saying, like, just intuitively for a moment, if you drop the squares, it's a little bit like saying the spread is equal to, well, no, it's not. The average squared is kind of like some kind of a baseline. It's like it's a midpoint in squared space, speaking very informally.
Right.
And the expectation of the squared values is then giving you kind of like an amount of spread, like not spread. It's giving you kind of distances in squared space. Like in squared space, how far does stuff extend? What's the average amount of like extension in squared space that there is? Is what this is, and then this difference is like that positioning in squared space from this
right from the
midpoint.
Yep,
this is like very informal,
but that actually does. I couldn't like that makes sense. In a sort of like in a fuzzy way that makes sense to me. Yeah.
Just calculate the squared average and the average squared, subtract and take the square root. Right. Since sigma squared is plainly non-negative, yes, 112 implies that the expectation of the square is greater than or equal to the squared expectation. Interesting. Okay. I'm gonna give myself some stuff here. Okay. Actually, I'm gonna try a thing. Let's see if this works.
Wow.
That's so cool. Oh man. All right. Oh no! I just ruined things. Okay. My little debug command. I executed a debug command that changed the state of the system pretty dramatically here, but it's okay. It's okay.
I wonder if there's a way you can do like a direct math fix to you like write in that box and you automatically have a math fix that.
Yeah. I think they have an API. Yeah, I really want to do that, particularly with universal control is a macOS feature from a year or two ago, which lets you move a macOS window over to an iPad. So I could like put this Chrome window on this iPad and then draw on it. Okay, I'm going to write a couple more.
While you're writing that, one thing that I think is interesting is, I think I probably looked at this the first time I went through it, and I'm like, oh, 3 lines is probably a simple theorem. They're just doing it for the sake of it.
Really?
But then, then going through it, it's like, no, it's not. It's actually something. If you had to do it from scratch, it's not.
A couple minutes.
Yeah.
Okay. What is that? So it's hard to express this kind of thing I'm trying to express right now in terms of a task. Let's see. I'll just write it, and I really do want what you're describing. All right, no, I'm gonna capture it. Yeah, it's such an interesting tool. Okay. And now I want to get the theorem itself. Okay.
Now, one thing I'm curious about is why this theorem is something that is interesting, because naively it doesn't have anything to do with quantum mechanics.
Yeah, exactly.
Yeah.
Clearly the author has a reason,
Mm-hmm.
and like we're about to use it.
Yeah.
And I don't know what that reason is, but I find it just interesting on its face enough to write down. So like I wouldn't normally do what we're doing here if I didn't just find it interesting from a perspective of like, wow, I didn't know this about probability. This was the expression in terms of sigma, not sigma squared, so I have to modify it. Okay. And I wish I could give myself, my little practice system doesn't have a good way for me to encode doing this proof, but that's something I want to explore. You know, I could make a task that's like do the proof, but it would be obnoxious, and I wouldn't actually do it. Okay, right. Now, first off, why does equation 112 imply this? I guess because we know standard deviation is real and not imaginary. Because sigma squared is plainly non-negative from its definition. Right, it's defined as the expected value of the squared deviations, i.e. the expected value of some positive numbers. And the deviations are, even if the deviation itself were complex because we're squaring it, it's real.
Yeah.
So sigma squared is plainly not just non-negative, but real and non-negative. I don't know if it makes sense to talk about imaginary numbers in this context at all, but I'm satisfied with that. And therefore, right, this property is true, which is interesting. Okay, the expectation of the square is greater than or equal to the square of the expectation. That's really not obvious to me. Okay.
This is another one of those things where if I spend 5 minutes thinking about it, I can I can see the intuition. But I think when I read it the first time, I'm like, oh, okay, that's a cool relationship. Fine.
Right. You just take it as given, right?
Right, yeah.
And that's like definitely one way to read textbooks, and I think it's like kind of fine. Okay. This is kind of an obnoxious thing to express as a question. So what I'm going to do is this. Just a little code for myself. All right, 7 questions. Let's just do them real quick. They have kinks, something like that. Angles. Can I even remember this? I just did it. So it is the expectation of the square minus the square of the expectation. Yes. And therefore, the expectation of the square must be greater than or equal to the square of the... Yep. Equals expectation AX. You can just push it in, drop the outers. Okay. And this is always 0. Not obvious. Okay. So far, I've assumed that we're dealing with a discrete variable. Those j's are integers. Let's look at continuous distributions. Now we'll bring some integrals in. All right. Right. If the interval is sufficiently short, this probability is proportional to the length of the interval. A random person off the street will have a probability that their age lies in some interval between 16 and 17. If the interval is sufficiently short, the probability is proportional to the length of the interval. For example, the chance that her age is between 16 and 16 plus 2 days is presumably twice the probability that it is between 16 and 16 plus 1 day. Yeah. Probably true, especially if you make the interval very short. Okay. Thus, okay, we're talking about infinitesimal intervals here. Proportionality factor, probability density. This is interesting terminology. Probability density is familiar, but proportionality factor is not. All right. So what is this thing? We define it in terms of some infinitesimal dx. Yeah. Whoop. Do I understand that? It's kind of interesting. So like rho x absent dx, what does it mean? It's like infinitesimal values, like gas. Multiplying by an infinitesimal value. Yeah, this is familiar. This is the kind of like mechanical thing that I know how to do with a probability density. What's kind of tripping me up here is this movement between rho x and rho x dx. I can see that like, yeah, rho x is like the infinitesimal version. It's the limit.
Maybe would it have a definition separate from dx? No. Maybe the two are together. Definition.
Yeah, I mean, like they're kind of setting it up to say that, like, I mean, empirically, like I know that it does. Like there are, you can get like a value of, like you can get a. If you look up the normal distribution, you'll get like definitions of the probability density function that like have values independent of a dx.
Yeah, that's what you mean.
I don't really know what they mean. And they vary from, well, the integral of it is 1, so it's kind of like, I guess it's the probability of getting x is actually, I see why people use that language. The integral of this thing is 1, so like it kind of represents probabilities, but you really do need to look at some range or some width to have something sensible to talk about if you're going to say that, all right, I'm not going to worry about that.
No, one thing I'm curious about there is I noticed that there's only one thing you've sort of like looked up so far using the GPT-4 tool. My default would have been just go on Quora and see what does P of X mean without D of X. I'm curious why you didn't.
I don't know. I think maybe this is still kind of a new tool. All right. Relative likelihood.
Whatever that means.
Likelihood is a technical term in statistics, I don't really know what it means though. Okay, I think it seems like they mean it informally. Local likelihood. Higher values mean the random variable is more likely to be. Okay, so it doesn't really have
an intrinsic.
The kind of like unit or something like that we might want. Its unit is not probabilities exactly.
This is something I didn't know. This is another one of those examples of something I would have kind of grazed by, like, oh, I get. I would just have seen this and I'm like, oh, I get that. And I wouldn't have realized, like, no, but what does each term there actually mean on its own?
It was really like the task of writing this made me grapple with the rho x dx distinction. Okay, so this I know. This is, the continuous version of the discrete version we got above. This is the continuous version of the discrete version we got above. That's familiar. Sigma, okay, this is the same thing from above. Okay. As he translated not for j, but for x. Sure. Assuming j was a discrete value and x denotes a continuous value. And we have another example. Suppose someone drops a rock off a cliff of height h. As it falls, I snap 1 million photographs at random intervals. On each picture, I measure the distance the rock has fallen. What is the average of all these distances?
This is a fun question.
What is the time average? All right. Yeah. Let's pull it out. I'm not going to look at the solution. What is the average of all these distances? That is to say, what is the time average of distance traveled? All right. Let's think about it. I assume we're going to use some of these identities. Oops. Okay, so we have some y-axis, and we start at some point h, and we drop a rock from point h, and then we're measuring the distance the rock has fallen, which is kind of funny. It's like an inverse axis, right? So we're actually kind of measuring distance from here. So I guess the natural thing to do really is draw another axis. I'll say let h be 0 basically, and we're gonna measure this distance down d or something like that.
Mm-hmm.
Okay, what is the average of all these distances? Well, one thing that we know is that the rock its position over time is not uniform, right? Like it's clustered at the top, and in particular, its motion over time. That's very sloppy. The rock's motion over time can be described by 1/2 mg squared minus 1/2 mg squared plus h. So that is its position over time. And we're interested in the average then of y of t minus h. H minus y of t. That'll represent the distance fallen. Yeah?
I wonder if that's the... Oh, yeah, you're right. Because given the unit t, it's automatically going to include the fact. Right, yep. That makes sense.
So, just by the definition of expected value, let's go ahead and try applying that from time t to infinity. T 0 to infinity. And the value will be h minus y of t. And what does that mean? The probability that it is at that position. I don't really know how to interpret this. dt.
But one thing I think we could, instead of infinity, we could just solve for what t will be at the end.
Yeah, that might help. I feel like the infinity is not yet a problem, but it is a thing to do, and maybe it will help.
But yeah, let's focus on what is the problem.
I don't know. Let's give it a try. Yeah. So when it hits the ground, I've done something very silly here in my. This is wrong. But this is not right at all. It's there. Okay. Now then, solving that for t equals 0. y equals 0, we would like to know the t such that 0 equals minus, not 1 over g, but 1 over 2 gt squared plus h, and that will be, well, I'm just going to do this the long way because I don't quite trust my working memory at this moment. I'm getting a little tired. Okay. Pardon me as I chug through some algebra here. Hopefully I haven't made any egregiously embarrassing errors. Okay. Does that help us?
Okay, I wonder the probability. One way to think about it is the infinitesimal change in y with respect to time divided by the total probability of it being at any point in time, which is 1.
Yeah, take the frequentist approach. Okay, yeah, right. So how do we right? So how do we think about p of h of t? Well, by the frequentist definition, it should be we could think of it as, the amount of time spent at that particular position over the total amount of time that is spent.
Yep.
I don't really know how to denote that.
Well, would it not just be dh minus yt divided by dt? There might be some reason why that's wrong.
Well, that's the change in this value over time.
I see. Okay.
I don't know that's not really the same as the amount of time it spends in that position. Were we given some nicer definition for, not really, the probability that an individual, I don't need to look at any of this. The probability that an individual lies between x and x of t. That's all we're given so far. We'd like, we're also given, I think we're hoping to be able to use something like no, never mind. We're trying to figure out what rho is. Okay. Well, we can write an expression for the amount of time that an object spends between point A and B. And then I think we can transform that to a probability by dividing that expression by the total amount of time it spends falling. So the amount of time that an object will spend between 2 points, A and B.
The integral of A and B with respect to dt. I know dt is at the end somewhere, but I don't know what goes in between.
Yeah, we need to invert this the equation of motion so that we can have an expression of t in terms of y. So let's go ahead and do the general inversion. I did the specific version of it over here. So actually your suggestion was helpful. This is the specific version for 0. And in general, if we would like to invert this, we have y minus h equals minus 1/2 gt squared, implying that t squared is minus 2 over g times y minus h, implying that t is the square root of this nonsense. It's not very pleasant, is it? Okay. And so I think that's where we're at.
You probably plugged that.
Did I unplug?
No. I just
I
the
can
metaphorical
plug it into the.
Yes,
I can plug this into the integral. So now we have something that we can integrate. So this is the time that the object spends falling. between y equals a and y equals b, we could transform this to distance fallen. Let's do that. So all right, I'm going to define d. Pencil. All right. I define d as h minus y, or maybe more formally d of y is h minus y. So now I can rewrite this slightly more neatly as the two negatives cancel, and we get 2 over g d, just 2d over g. d. And now we have a tractable integral, which I'm feeling a little rusty on. So we have something to the 1/2 power here, which means we're going to end up with something to the 3/2 power, and it's going to be multiplied by
3/2.
3/2. Also by 3? By
Oh, sorry.
By 2 thirds?
Yeah, 2 thirds, right. Yeah. You
by 2
1
thirds,
over,
right?
Yep.
So we have 4/3 g d to the 3/2, maybe. I feel not very confident about that.
The 2 is inside the. Can you distribute it because it's inside the square root?
No. We have a more complicated expression. Thank you. We have 2/3 times 2 over g. I'm not doing things right here because you get there's a chain rule for the interior. So I'm going to turn to Wolfram. This is very embarrassing. I really should be able to integrate this, but I simply don't remember. And let's just make this easier.
This may be a good opportunity to ask one question I was curious about, is that when do you decide that, I mean, here you know what you're trying to solve for, and this is something that if Wolfram Alpha can solve it, what is the rule for when you could decide to go through it yourself and when to do it using Wolfram Alpha?
Oh, I'm not trying to learn calculus here.
Yeah.
Like, I probably should know calculus well enough to do this. It's like not at all obvious to me how this comes out the other side. So clearly I need to brush up on my calculus. Like, geez, come on. That's pretty embarrassing, I gotta say. Like, there's an extra, a D term here on the outside. I think that comes from the chain rule. But yeah, it's like pretty embarrassing. I should be able to do this. All right. By the way, MathPix has this like kind of crazy thing.
You can just solve it by putting it in?
I mean, we'll see. Let's see.
Wow.
Awesome. Yeah. Awesome. A notably different solution. I don't know how I feel about that. Why is it different? Is it different?
Result equals 2.
I think it's probably different. B.
Where does B?
Where does B come from? Oh, A and B. Oh, because this is on the right is an indefinite integral. Okay. Please instead. Can you let me edit it? Can I edit it? Okay.
Nice.
Maybe? No, we still got a different answer. So there's the 5 over here and a 3 here. Why do we think this is?
Is it possible that the DD is confusing it?
Yes. But I'm actually more skeptical about the 5. Like, where did this 5 come from? This is like 5 is a prime, so it's not like we got it by like some kind of multiplication of the 2 by...
It could be that common divisor and combining that.
Something embarrassing is happening here. Wait. Okay, there's an extra... yeah. Okay. By x. It interpreted by x as right. Multiplied by x. Okay, now we get the same value. It's something simpler. Okay, great. I'm glad that we double checked it by trying to... All right.
Right, and divided by the total time.
Right. Okay. And now we don't have this weird 3 halves. Why don't we have 3 halves? That's interesting. Oh, we do actually. Mm-hmm. It's just they've kind of simplified. We also don't have this G.
Yeah, I was about to ask, where did the G?
Yeah, it was in the previous solution. Okay. This is a kind of a weird way to express this. Like, I found myself wanting to rewrite this as 2/3 times, like, root 2 over G times D to the 3 halves. Get all the constants together. Mm-hmm. I don't know. Okay, so we have this ugly thing. Like, it's the distance following times a constant. So this is good. So now I think we can actually go ahead and write the probability that it's between A and B is this quantity over, my dog insists on attention, over this other quantity, and over this other quantity, the total amount of time. And I think we're going to get some nice canceling. So first, let me go ahead and rewrite this guy in terms of D, because now we're going to get, sorry, we don't have the negative. Yeah. Okay. So I can see already some nice stuff's going to happen. We get 2/3 times root 2 over G times D to the 3 halves over root 2 over G. And I'm going to go ahead and write this in a way that's going to make my life a little easier. My pencil will cooperate. Okay, times root D.
Yeah.
And I'm going to go ahead and rewrite this
D is 1/2.
As D is 1/2. That'll make it easier for me. And now we're going to get something really pretty nice. So we get just 2/3 D, right? Does that look right to you?
Mm-hmm.
That's lovely. Okay. So now...
I think that's the answer.
Wait.
Because, so...
is that what we're solving for? What are we
solving
for?
I don't think this...
we're solving for the average. Hang on.
Yeah, that's the average. The average distance is going to be 2/3 times the total distance.
Well, okay. That's an interesting leap that you've made. I'm not ready to make that leap. I'm not quite sure how you've made it. So let me go ahead and satisfy myself that if I plug these things in. So to find the average, we're going to integrate from 0 to infinity of d by p of d dt. Wait, where did the a and the b go?
So what I'm thinking is we already have, so in this equation here for the probability density, I'm actually not sure what P of X means in this context, but we already have P of AB, which is on the left hand, right? Or what you just replaced here was P of AB.
Yeah, it was. Now I'm confused.
So that
is the
final form. But I see what you're asking. Like, what would it have been if we did it there? If we had plugged in.
Wait.
So like, it's not rho; it's the large P. But what is rho? Is that?
We have rho. Rho is wait. I messed up. That's not what this is. This is rho of D, because through the frequentist interpretation, It is the amount of time spent. No. It is PAB. It is PAB. But I don't know what AB means. I'm confused. Oh, it's P0 to infinity. That's what it is.
But you already.
No.
Oh, I see. Yeah,
I'm very confused. Oh, I've just done something completely ridiculous. Like, look back here. I took this this definite integral,
and you turned it.
And I used an indefinite integral solution.
Uh-huh.
This is nonsense. This is total nonsense. So we actually wanted the other form that we were given, right?
So actually, I'm kind of curious if we just sure. Since we have this, what we have is just t, the total time spent in terms of distance. Because if we did it in the indefinite integral terms.
Well, kind of. You need to plug 0 and infinity, I guess. No, but they're distances. It's not time.
Hmm. So if you
so 0 and h.
But 0 is going to cancel out, right? So
0 is going to cancel, so we'll just have h.
Yep. So it'll be 2/3 h squared to do it from the beginning to the end.
Yeah.
No, wait.
Question mark. Also, I'm very confused on the.
Oh, you're just subbing in h for d, so it would just be 2/3 h. So 2/3 h is the total time traveled.
Yeah. 2/3 h is the total. Yes, I agree. I've done something very strange over here as well, I realize now. But yes, 2/3 h is the total time traveled. That seems.
And so 2/3.
I really should revise all this stuff in the middle. This has become quite a mess. But
all these distances. If that's a total time travel, then the average would be that divided by. No, that doesn't sound right. 2/3 h.
We're getting close to something here.
Would it just be 2/3 h divided by t? Would be the average time. Average of the distance traveled. No, wait.
Well, there's this other weird thing where, like, actually, I think what we this is slightly wrong. So look here at this term. This should actually be rho, not p.
I can't see it in here. I think it's covered up by.
Oh, it's covered by this mathpix thing. Okay. So I had p here. Let me write that again. I had p here, but that's actually not right. I think it should be rho. And the two are different insofar as p is an integral. Mm-hmm. So putting p there is kind of a type error. Like rho is the thing that gets integrated. Yep. And okay, so we're still struggling to define rho here. We don't quite have a definition of rho. We have a definition of p, almost, kind of, sort of.
Yeah.
If we were to actually what needs to be done is evaluating this from A to B. And we noticed, or you noticed, that there's maybe we can skip some steps here if we apply the special case of 0 to h. But if we apply that just gives us the total time, right? Like that just gives us this thing that we already figured out.
If we have a
So I think there's more grunt work to do, unfortunately. Miasma of wrongness kind of extends. Okay. All of this is touched by a miasma of wrongness. I did something very strange here on the right also. Actually, hang on.
Wait, is it?
No. I think this thing on the right is fine.
No, actually, the way we're in reverse wrong might be the way, because what we ended up doing here is just divided by the total time. Wait, no.
We were trying to get the probability that it's between A and B at a particular time.
Right. So I guess if we just back up, what is the probability that?
But we actually want something different. Like we need rho. We need this probability density. And can we get that probability density from the probability that it's between A and B? I guess we could invert this. So I guess it's the case that like, well, yeah.
Oh wait, so I'm still hung up on this because the probability that it is at time t equals the probability, or like the probability that it's between okay. No, keep going on your track. I'll see if I can think.
I'm realizing I also don't quite know how to invert definite integrals. Clearly, I need to brush up on my calculus. Yeah, it's not totally clear what I mean. Thank you, GPT-4, for taking a broad interpretation of what the hell I might mean. So broadly what I'm thinking here, Dwarkesh, is that like, I think we know how to find PAB.
Yep.
And we would like to find rho so that we can eventually find this thing.
Yep.
I also get the feeling that we're doing something much more complex than what this example is doing.
Yeah.
But you know, I'm going to scroll down. Look at this. Oh no, good. It's not over. Okay, this is a somewhat longer thing. Total flight time. Root 2h over g. Yeah, that is what I found. Okay. The probability that it was taken is dt over t. Statistics. Okay, they don't try to actually calculate it. They just express it with an infinitesimal using the same kind of... This is some calculus rustiness here. This is a very uncomfortable move for me. Okay, I will need to stare at this for more time to actually understand it. It's interesting that example 1.2 is already straining my prerequisites here, and it seems like yours as well.
Yeah, no, and it's even more embarrassing for me because I looked through this.
We're like, yeah, seems good.
Yeah, exactly.
Exactly. And maybe it is. I mean, that's like an interesting thing about studying in this way.
Yeah.
If you actually insist that you understand everything, that maybe you fall down some rabbit holes that you don't need to understand, although, you know, seems like if one wants to claim that one has understood the contents of this book, one should probably understand the concepts. I don't know. So, do you have wrap-up questions we should ask?
Well, one thing I'm curious about is I remember when I was doing the Fast AI course, the instructor said that one failure mode that students fall into is that they'll see some function, they'll see like cross entropy, and they just like define, and they'll be like, why does it work? And the instructor said this is a failure mode, that what you should actually do is just do the exercises we've given you, like where it says to do, and you'll get to all this later or something. I'm curious how you think about.
I think that's not a terrible idea. I wrote an essay a long time ago called Top to Bottom, Bottom to Top. That was making kind of a similar case. I don't know what was that Jeremy in his book?
Sure.
I don't know what his like rationale for that claim was, but kind of inferring a rationale. If the idea is that, I don't know, motivation is like a most important thing.
That makes sense.
Like you want to take that which is precious and kind of fuel it, and like you're excited if you're taking Fast AI to like build stuff. So you should build stuff and like get pumped and like get interested and get facility, and you should use that fuel later to actually understand stuff. I mean, I suspect most Fast AI students don't do that thing, and that's maybe fine for them as like people who are building stuff with models. If the goal is to understand the stuff, I think there's some amount of I will leave this for now and come back to it later that's appropriate. And I guess like I'm very sympathetic to and trying to be very sensitive to like my motivation in a given moment. Like, what am I interested in? What am I trying to get out of this? Like, what do I care about in this moment? Like, we just got bogged down in a bunch of like not knowing calculus well enough. And, you know, maybe to some extent, some like not being super familiar with probability identities. and like how material are those things to the study of quantum mechanics? I don't actually know in this moment, and my recollection is that they're like pretty material. And so if the aim is to understand quantum mechanics, then like probably we have to understand those things.
Yeah. That makes sense. But yeah, just like a closing thought for me is just like I didn't realize how different this approach to reading a text and trying to like actually understand it. It's the difference between like reading some pseudocode that's not even in a programming language and actually understanding the assembly language that implements it,
or at least trying to understand it, as we just experienced. It can sometimes be difficult. Well, thanks for doing this with me.
Yeah. This is a lot of fun. This is really inform how I study not just this material but other stuff in the future.
Cool.
Yeah.
Thank you.